Okay, class, it's on to the brain. You guys already know I am in love with Alex Gray's drawings. I love Alex Gray. The mind's eye, the brain. The brain is seeing what it's seeing because that's the brain. The way it interprets things, that's the brain. I love the brain too. Anyway, let's get started. Just some general info on the brain. Here is a close-up of a living brain. This was taken during surgery. So they were doing some kind of operation on this patient. So this is the brain up close. You can see the contours of the brain, the blood vessels all throughout the brain. Way cool. We talked about the neurons in the brain. What kind of neurons are in the brain? Those are interneurons, multipolar interneurons. Each neuron can process information up to 200,000 different sources at one time. So lots of connections. Each neuron is talking to thousands upon thousands of other neurons throughout your brain. Now, I just looked this up. This is real. 86 billion neurons in an average adult brain. Some of you can have less if you've destroyed some of your poor neurons, but on average, we have around 86 billion neurons. This isn't something we don't know. The brain contains 95% of the total neuro tissue in our body. That makes total sense. The average weight of an adult brain is 3 pounds. 3 pounds. But the weight that you actually feel by your neck and muscles holding it is only 1.7 ounces. And that is because, remember, the brain is suspended in CSF, cerebral spinal fluid. So floating in that fluid, it's going to lessen the weight that our bodies feel. Now, this part, the brain consistency, is that of soft tofu. Some people say it's like gelatin, soft gelatin. I had one person said it's the consistency of ripe avocado. So no matter what they say, you know it's very, very soft. It's soft and squishy and easily damaged. So it's a very delicate organ. Yes, it is. And our neurons are very demanding. We've already talked about them. They have a high metabolic demand. The brain is going to suck up 20% of your cardiac output, meaning every time your heart beats, 20% of all the blood flow is going to go to your brain. And it needs lots of blood sugar, glucose. It needs glucose. 30 to 35% of your blood sugar is going to the brain. That is your neurons. So how are we going to protect this delicate organ? The bones of the skull, we already talked about that when we did the cranial cavity. What's inside the cranial cavity? The brain. So outside protection is going to be the skull. Now, deep to the skull, we're going to have our cranial meninges. And we talked about the cranial meninges with the spinal cord. It's going to be the same 3 meninges with one modification in the dura. And the CSF, that cerebrospinal fluid. Oops, I forgot my little space between cerebrospinal fluid. and that is going to include the ventricles of the brain. We have not talked about the ventricles of the brain. I'll show you them a little bit today, but I don't think we're going to get to them today. And our blood-brain barrier. We talked about how our astrocytes are helping to form our blood-brain barrier. So I put down here we're going to discuss the meninges, the ventricles, and the CSF. I don't think I'll get past the meninges today, but let's see how far we go. So, the three meninges, same as the three of the spinal cord. The dura mater. So, meninges means membrane. And dura is Latin for, well, mater is Latin for mother. I think I told you guys it was German. I'm sorry, it's Latin. Dura mater is hard mother. Dura, durable. The arachnoid matter is a delicate web-like membrane. Remember, arachnoid means spider. So the arachnoid looks spider webby like. And the pia mater, this is what is clinging to the brain, the contours of the brain. It's a real delicate, transparent connective tissue. So let's look at this. So here we have we see the dura. Here we see the skin has been pulled back. Here is the skull. They've sawed off the skull and taken off the top of the skull, and this is what you're going to see. This is the dura, a dense, fibrous connective tissue layer. Now, in the brain, this dura has two layers. This outer layer that you see is called the periosteal layer, and it's adhering to this cranium, the skull. So the periosteum of the bone, this is the periosteal layer of the dura that is next to the periosteum of the bone. Deep to this periosteal layer is another layer called the meningeal layer. And that meningeal layer is what you're going to find in the spinal cord. The spinal cord does not have this outer periosteal layer. Here is another view of the dura. This is the ear, so this is a side lateral view. This is the front. This is the back. So here we see the dura. Here you can see the bone of the skull. Here you see some muscle, and then this is skin outside here. So the dura is supplied by these middle meningeal arteries. Now, these arteries can be damaged, and you can get a hemorrhage from these arteries too if you have head trauma. And you can get an epidural bleed if these start bleeding. Epidural bleed, what does that mean? A bleed above the dura. So epidural bleeds are going to be above the dura. So I think that's about all we can see on this slide. Here is another slide of the same thing, also a lateral view, front, back, the dura, the middle meningeal artery. Here you can see the skull up here, and here they still have the hair and skin. Pretty cool. Now, deep to the dura is going to be our next layer, the arachnoid. Get this picture over here a little bit. Arachnoid, like cobwebs of a spider. It's a delicate web-like membrane. So once you've taken the dura, here's the dura, they've cut it and reflected it back. This is what you're seeing. Now, obviously, this is a cadaver, so the you're not seeing the remember in the subarachnoid space, subarachnoid means deep to the arachnoid, you're going to have the CSF flowing. Well, there is no CSF flowing in this brain because obviously this person has died and all the CSF has been drained out. But you can see the arachnoid. It's a fine web-like membrane, and you can see the contours of the brain beneath it, but it's kind of a little hazy. And remember, deep to this arachnoid is the subarachnoid space. You have to remember that. Subarachnoid space. What's in the subarachnoid space? CSF. So this is another view. Here we have the skull again, the bone. Here you can see the dura. And now here you can actually see where the dura is splitting in two. So we're going to have what we call a dural venous sinus, and I'll talk to you about those shortly. And those dural venous sinuses, they're going to be formed by the separation of the dura. So here we have dura together, and then we're going to see a separation. Here is going to be the periosteal layer of the dura, and then here is going to be the meningeal layer. And in between, there's going to be a space. And we'll talk about that shortly. But I just want to show you that on this diagram. Here we can see the dura here. And here is the subdural space. Subdural, beneath the dura. Subdural space, you can have subdural bleeds in here also. What else can I show you on this? I think that's it on this picture. Now, this is from a dead person too, but this is from an autopsy. So this person just recently died, and you can actually still see CSF within the brain. So here's the dura being pulled back. Here's the arachnoid, this glistening membrane. But what do you see deep to the arachnoid? Can you see this green stuff where it looks like there's green fluid in there? That is pus. What is wrong with this patient? This patient died from a bacterial meningitis. This is full of pus. Meningitis, inflammation of the meninges. This is bacteria. This is a swarm of pus flowing in the subarachnoid space in that CSF. Now on this picture, this is the front of this patient. This is the right hemisphere of the brain. This is the left hemisphere. Here's the dura being pulled back. We are seeing this structure, and we'll get to this shortly too, but since it's here, I'm going to point it out to you. This is called the falx cerebrae, and the falx cerebrae is made from dura. I'll show you that shortly. And this falx cerebrae is actually separating the two hemispheres of the brain. It's going right down the middle, and it's separating the two hemispheres of the brain. But I'll show you that in more detail a little bit later. So on this diagram, they have now removed, obviously, the dura is gone. The arachnoid is now gone. And what's left is the pia. So the pia mater is clinging to the brain, and it is going into all these crevices. There's grooves and crevices in the brain that we'll talk about shortly. Not today, but all these contours of the brain. So the pia is going in all those contours. And here's all the blood vessels that are on top of the brain itself. On this picture, besides seeing the pia, I want you to look at these blue blood vessels. These blue blood vessels are the venous blood vessels of the brain. This is all deoxygenated, used up blood by the brain. These venous blood vessels are going to be traveling towards the midline of the brain. Right in the middle of the brain, in between the two cerebral hemispheres, is going to be a blood channel. This is a blood channel. This is going to be a dural venous sinus, and I'll show you that shortly. But here you can actually see these blue blood vessels going into it. If you look close right here, you can see the dura, this white stuff. Now the dura is separating. I don't know if you can see that. It's separating up here, and then here's the bottom layer. So this top layer of the dura that's right next to the bone is the periosteal layer of the dura. This layer down here is the meningeal layer, and in between is going to be venous blood. So all these blue blood vessels are going into this venous blood channel. So now we're going to talk about the dural venous sinuses. So when you see this dural venous sinuses, this is telling you everything you need to know. Dural, it's made from the dura. Venous, it's carrying venous blood. In this case, deoxygenated, used up blood. It's in a sinus. What's a sinus? A sinus is a space, a cavity in our bodies. So this is a space that is carrying venous blood, and it's made from dura. Now, we already said that the dura of the brain has two layers. We have the outer periosteal and the inner meningeal layer. And in some places, these two layers are going to separate, and they're going to form a space. And that space is going to contain the venous blood. And those are our dural venous sinuses. So the ones you need to know are going to be the superior sagittal sinus that will be easy to see, the transverse sinuses that will be easy to see, the sigmoid sinuses that you won't be able to see, and these sigmoid sinuses will then take that blood to our internal jugular veins that you already know about. So let's have a look at this picture. So this is posterior. So this is going to be the occipital lobe. Here is the cerebellum. So this is the back side of the brain. Here is the superior sagittal sinus. It is in the sagittal plane. Remember, this is the mid-sagittal plane right here. It is separating the left brain from the right side of the brain. So it's a separation. Superior sagittal sinus. So this venous blood is going to be directed into this superior sagittal sinus. The superior sagittal sinus will then take that venous blood into either the left transverse sinus or the right transverse sinus. So easy to see on here. So let's do like a coronal section, a frontal section of this area right up here. So we are seeing the bone here, and this is going to be where we have our superior sagittal sinus. So let's see if we can make sense of this. Here is our dura. We have both the periosteal and the meningeal layers fused together right there. Now they're going to separate. Here's the periosteal layer. Here's the periosteal layer of this side. Here's the meningeal layer coming down. Here is the separation of the meningeal layer on this side. The meningeal layers are going to come down and form a structure called the falx cerebrae that we'll talk about shortly. But in between the periosteal and the meningeal layers, we have this opening, this sinus. This is going to be our superior sagittal sinus. This is going to be carrying our blood. This falx cerebrae that is now formed from the meningeal layers it is separating the left and right cerebral hemispheres, and we'll talk about that shortly. Here is a drawing of what you just saw. Here's bone. Here's the two layers of the dura. And then you can see the periosteal layer next to the bone. And then here is the meningeal layer. Deep to the meningeal layer of the dura, we're going to have the arachnoid, the dark purplish structure. Deep to the arachnoid, we're going to have the subarachnoid space, where you see all these little web-like connective tissue fibers. These are called arachnoid trabeculae. You don't need to know that, but that's what they're called. This is where CSF is flowing, right here, in these web-like spaces, the subarachnoid space. And here is the falx cerebrae again, formed from the meningeal layers of the dura. We'll talk about these structures when we get to the creation of CSF and its circulation and reabsorption. But these are arachnoid villi, aka arachnoid granulations, and we'll talk about those later. But here, this blue thing, that is the superior sagittal sinus. Superior sagittal sinus running right down the middle between the two hemispheres of the brain. Now this is way cool. You've already seen this, superior sagittal sinus, transverse sinuses, right? So here's a venogram. So this is actually someone's big venous sinuses. They've injected them with dye. You can see all these venous blood vessels going to the superior sagittal sinus. Superior sagittal sinus is going to split into a left and a right transverse sinus. And then those transverse sinuses are going to turn into sigmoid sinuses. The sigmoid sinuses, remember sigmoid is curvy, like an S shape. And then the sigmoid sinus is going to deliver that blood to our internal jugular veins. So the flow of blood out of the brain is going to be superior sagittal sinus, transverse sinus, sigmoid sinus, and the internal jugular veins, right and left internal jugular veins. Here's a diagram just so you can see it. Again, here is the superior sagittal sinus that you need to know, showing you the transverse sinuses. Here is showing you the sigmoid sinus, and then the sigmoid sinuses are going to dump that deoxygenated, used up blood into the internal jugular veins. Where do the number one, what hole are they leaving the cranium from? They got to get out of the skull. What hole are they leaving the cranium? Remember your jugular foramen? So these internal jugular veins are leaving the skull through the jugular foramen. The internal jugular veins are going to take that blood to where? To the left and right brachiocephalic veins that are going to be taking it to the superior vena cava, that will be taking it to the right atrium. You should know that. Here's another picture. Pretty simplified picture, but it's easy to follow. Superior sagittal sinus. Here's the left transverse sinus going into the sigmoid sinus, turning into the internal jugular vein. It's leaving the skull through the jugular foramen. That left internal jugular vein is then going to be dumping its blood into the left brachiocephalic vein. which takes it to the superior vena cava and back to the right atrium of the heart. So here I want to talk to you about dural reflections. So there's areas within the skull where the meningeal layer of the dura mater folds inwards has dural reflections, and they partition the brain and divide the cranial cavity. What does that mean? Well, we've already seen one. You've seen the falx cerebrae. So here we have the dura, the periosteal layer, and then the meningeal layer. Here's the superior sagittal sinus, and here's the meningeal layer coming down on this side, the meningeal layer coming down on this side, forming the falx cerebrae right in the middle that's dividing our two cerebral hemispheres. This is the falx cerebrae. It is made up of the meningeal layers. Hopefully you can see that. And there's going to be another one down here called the tentorium cerebelli. Tentorium cerebelli. Now the tentorium cerebelli is going to be next to the transverse sinuses, and this is going to be separating the occipital lobe, the back side of the brain, from the cerebellum. And I have plenty of pictures to show you. So don't think you have to figure it out by looking at this. I don't expect you to. So let's first look at our falx cerebrae real closely. This one we've already seen. Dura, periosteal and meningeal layers fused. Here's the skull bone, and now they're separating. Periosteal layer, meningeal layer. Meningeal layers come together to form this falx cerebrae. We've already seen this, but let's look at it closer. Now, I'm going to take this pretty slow. So this is way cool. But let's zoom in and look at these from number one. Let's go to A. Let's look at this. Let's zoom in on this right here. What are you looking at? Here, this is an autopsy. So this patient recently died. So this is going to be the front. Here's the chin of the patient. Here's the ear. Here's the backside. So here they have cut the skin. So the skin is draping over. They removed the top part of the skull. Here's, you can see where they sawed it. So here's the bone of the skull. They've cut through the dura. Here's the dura. They've reflected or pulled that dura back. Here's the arachnoid. So you can see the glistening arachnoid. You can almost see there's still some CSF deep to the arachnoid. So here's the contours of the brain, right smack dab in the middle. This is the falx cerebrae. So he's pulling it up. He's pulling that falx up. So hopefully you can see it. It's attached in the front here. So you just can't pull it all the way out. He's going to have to cut this to remove it. But it's attached in the front and it's attached in the back. So let's go to our, if I can get over. So now, where are we? This is the back side. So this is the back of the skull. Here's the true cerebral hemispheres now. So now you can see both of the cerebral hemispheres. And he's pulling up the falx. He's pulling up the falx in between them. And you can kind of see right here, it's separating right here. So this is going to be a dural venous sinus right in here. So it's separated right there. don't know if you can appreciate that, but this is the falx. Now let's go to our third picture. Oops. This one is going to be hard for you to visualize, but let's see if we can walk through this one. So this is the front. This is the front of this I don't want to call it patient, but this person. So here we have the dura, and here's going to be our superior, here's going to be our superior sagittal sinus. You cannot see the top part of the dura very well right here, but here is the meningeal layers of the dura coming together to form this falx in between our cerebral hemispheres. So you can see how soft and squishy the brain is right here. He's barely pushing down, and it's just like, just mushy. But he's pulling it down to show you that this is attached. Here's the front. So to remove the brain from this patient, he is going to have to cut the falx to get the brain out, and that's what he's going to do. So let me show you what he's done here. So he went ahead and cut it. So he's now, the brain is loose. The brain is loose. Why am I showing you this? So here's the patient's ear, here's the patient's chin. The brain is now loose, and he can remove the brain. Now, this is from the same, I'll just call this person a patient. This is from the same patient. He has removed the brain from the cranial cavity, and he's reattached the falx cerebrae from the front part. He had to cut this. Remember, he had to cut this to take the brain out, but he sutured it back together so you can actually see the entire falx, the way it sits in the brain. This is way cool. And then here's going to be the tentorium cerebelli. So here's the falx cerebrae. It comes back, and then where it's going to go to the right and left, we're going to have this falx cerebrae. We're going to have the tentorium cerebelli, and I'll show you that shortly. But what I want to do is I want to go in closer here. Oops, now I moved this pointer. Here is our falx cerebrae at the front end. It is attached to the crista galli. Remember the crista galli of the ethmoid bone? That thing that's sticking straight up? You can see the holes of the cribriform plate right here. So the crista galli is there to have the dura attach at that point. So that is way, way cool. What else can you see in this besides the cribriform plate? Here's the sella turcica right there. Way cool. So here is another demonstration of the same thing. So here we have the dura it's been cut and pulled down. Here is the two cerebral hemispheres. Here's the backside. This is the occipital lobe. Here they have cut the falx cerebrae, and they are lifting it out. So this is the falx cerebrae. Remember, this is made just from the meningeal layers. Up here is going to be containing the superior sagittal sinus, that's the blood channel. So down here, the falx cerebrae is going to be connecting to the tentorium cerebelli. The tentorium cerebelli, we can't see it here, but I will show it to you shortly, I hope. Here is, so the dura, this is just the falx cerebrae in there. It's coming down. Here is our transverse sinuses. So here is the periosteal layer of the dura and the meningeal layer of the dura and these transverse sinuses. So remember, this is the transverse sinus. That is an opening where we have blood flowing. Here is the tentorium cerebelli right here. So this is formed from the meningeal layer. That is separating the cerebellum, this part of the brain, from the occipital lobe up here. Here are some more pictures. This is from, hopefully you can see this one. Here's the anterior, posterior. So this is all the falx. Here's the tentorium cerebelli on the back side. So I want to show, well, the reason I'm showing you this is the falx does not divide the two hemispheres all the way down the middle. It's going to stop. It's going to be stopping at this structure right here. So here's the falx and it stops. So if you look at this, here is the falx. It's not real deep. It's not dividing the entire, the two hemispheres all the way down the middle. It's stopping. It is stopping because it has to have this structure. This is the corpus callosum. Now we'll be talking about the corpus callosum a lot when we get into the brain, but this corpus callosum is basically white matter. It's a white matter tract, and it contains millions, if not, it might have billions, I'm not sure, of axons, myelinated axons. This is all white matter. This is how the right hemisphere communicates with the left hemispheres. The right and left hemispheres are separate except for this white matter tract connection. So the falx is stopping there because we have to have communication between the right and left hemispheres of our brain. Here is a diagram that's in most textbooks. So here you see the falx cerebrae. Here is the tentorium cerebelli, that horizontal shelf that's separating the cerebellum that lives down here from the occipital lobe that's back in here. This is showing you the superior sagittal sinus. Here is a transverse sinus that would be coming out towards you if this was 3D. Here's the transverse sinus going into the sigmoid sinus. So here's the transverse sinus. Here is it in a cadaver, falx cerebrae. So you can see it stops. It's not going all the way down. Falx cerebrae. Falx cerebrae. Here's the tentorium cerebelli. This piece of the meningeal layer of the dura. Here is the cerebellum. You can see that. Here is the cerebellum. So this this tentorium cerebelli is separating the cerebellum from the occipital lobe of the brain. So just I don't know why I'm going on so much about these. I want you to cry uncle and say, I got it. I got it, Dr. Sweet. Here is what? What is this? The falx cerebrae. Here is showing you the tentorium cerebelli, who sits here. It's going to be their cerebellum. So this is the front. I'm trying to find, here's the ear. This is going to be the front of this cadaver. Here is the falx cerebrae. Here's the tentorium cerebelli here. Here is the corpus callosum, and these are going to be deep midline brain structures. Here it is on a cadaver that's been sawed right in half. Here you can see the corpus callosum. This is going to be one of your lateral ventricles right here. So the falx cerebrae member starts here, goes all the way to the back. Here is the tentorium cerebelli that is separating the cerebellum from the occipital lobe. Remember, the falx does not go past this corpus callosum. It stops. The falx is only going from here to about here. Here's your brain model that we have in the classroom. This is showing you the corpus callosum here. Here's a real brain. Here's the corpus callosum. Here's one of your lateral ventricles. So corpus callosum, occipital lobe, cerebellum, falx cerebrae goes from the front all the way to the back. Then we're going to have the tentorium cerebelli right in through here. The falx cerebrae does not go past this corpus callosum. If we were in the classroom, you would be doing this. This is a sheep brain dissection. Here the student has cut off the dura. You can see the dura up in here. And here's the left hemisphere, right hemisphere. Here's the cerebellum back here. So when you pull the two hemispheres apart, they do not come apart. They are held together by this corpus callosum. Remember, corpus callosum, white matter tracts. This is how the right and left brain are talking to each other. They're sharing information through this white matter tract, the corpus callosum. So this is just going to be a little review. Here is the dura. Here is the superior sagittal sinus. You can see some clotted blood in there. Transverse sinus. Here you can kind of see some arachnoid still covering the spinal cord down here. But remember, the spinal cord has the same meninges as the brain, except for the spinal cord does not have the periosteal layer. This is just the meningeal layer, the dura that is coming down to wrap around the spinal cord. Here they have removed the dural sinuses. So up here again, you can see the superior sagittal sinus. Here is the falx cerebrae coming down. Here is the tentorium cerebelli, that shelf in there that's separating the cerebellum from the occipital lobes. Here you're seeing the end part of the transverse sinus here. There's the opening of the periosteal and meningeal layers. Remember, the meningeal layers come together to form the tentorium cerebelli. Same thing on this side. The dura separate. So we have the periosteal layers and then the two meningeal layers to make that tentorium cerebelli. They've cut a little bit deeper here. So now once again, you're just seeing the superior sagittal sinus, falx cerebrae, tentorium cerebelli. You're seeing the transverse sinus where this is the meningeal layer that's forming the tentorium cerebelli. Hopefully by now you're going, I can see this, Dr. Sweet. I see it. Here is the deep layer, deep structures of the brain. We're going to go the brain stem. So here we can see this is going to be the foramen magnum, and this is all spinal cord down here. Now, we're going to leave with a bang. I've been talking for so long. why am I stressing all this? This is a closed box. Your brain lives in a closed box, and it is vulnerable to any pressure. Can you imagine if you had a tumor in your brain that was growing and pushing down on that gelatin or tofu soft brain? What's going to happen to the brain? The brain is going to be compressed. So if you have any kind of pressure that is pushing on the brain, it can cause problems and can cause death. If you have a bleed, there's a lot of blood collecting. Where's that blood going to collect? If you have, we're going to be looking at a subdural bleed. If you have a bleed below the dura, where's that blood going to go? On top of the brain? And it's going to collect, and what's it going to do? It's going to start pushing down on the brain. Where can the brain go? This is all bone, hard bone. Where's it going to go? It's going to go here. So if the brain is being squished down through this hole, and here's the brain stem, you can see this is what they call brain herniation right here. Here's normal. You can see here's the corpus callosum. This is the brain stem. Here's the cerebellum, and here's the foramen magnum. Now, the foramen magnum, this part of the cerebellum and the brainstem is being pushed into the hole, the foramen magnum. This will cause death. So let's see what that looks like. Here we go. Acute subdural hematoma, subdural, beneath the dura. 83-year-old female, head trauma. She had herniation, it basically means brain herniation, severe intracranial hypertension, meaning lots of pressure, intracranial pressure. Here's the bleed. It's pushing against her brain. This is supposed to be midline. All these midline structures have been shifted over. Severe, lots of pressure on this brain. This is supposedly showing you the herniation through the foramen magnum. Here is her skin. So her hair has been shaved. They're pulling off the skin. They are pulling it over. Here is the skull. So they're going to have to saw through the skull. And they will remove the skull, the top part. And there is the dura. So they have to cut through, remember, cut through the dura. Tough dura. And what is beneath the dura? We've got the subdural hematoma. Look at that. Lots of clotted blood there. So they're going to remove that. Now they have to find the bleeding source. Where is the blood coming from? Can you see the blood? Can you see that blood squirting up right there? Look at that arterial blood just squirting up under high pressure. So they've got to make sure that stop it from bleeding. Then they reassess, make sure there's no more bleeding. They are going to have to reattach that dura. They're going to sew the dura back together, and they will eventually put the skull, the bone, back on too. That is way cool. So hopefully you guys learned a lot, or hopefully you learned something, and now it'll be on to the brain.